All right, this will be part 2. We're going to look at a really quick worked problem where we're dealing with a very weak acid that's a diprotic and how to solve those problems. So let's ask this question. Let's calculate the pH of a 0.1 molar carbonic acid solution at 25 degrees Celsius. Now, Ka1, the first deprotonation of carbonic acid, Ka1 value is 4.3 times 10 raised to the negative 7. Ka2, second deprotonation value, is 5.6 times 10 to the negative 11. Now, we're dealing with a diprotic acid, so let's first write the reaction for the first deprotonation. So I have carbonic acid reacting with liquid water to generate hydronium ions and bicarbonate ions. And I can fill out my rice table. This is 0.1 molar. I don't care about liquids. 0 and 0. Change. Minus x. I don't care. Plus x. Plus x. And at equilibrium, 0.1 minus x. I don't care. X and x. Now, unlike in the situation where we were looking at sulfuric acid, where sulfuric acid was a strong acid, I definitely had to worry about X. And unlike my situations where I had very small values, or rather very large values of K, in this situation, just like with our other weak acid problems, since my Ka is a significantly small value, this is 10 to the negative 7, and our cutoff is 10 to the negative 4 or smaller. Since K is very small, that implies we are favoring reactants at equilibrium. K is very small, which means very little of the reactants are getting turned into products. So very little reactants are getting turned into products, then X is going to be a very, very small number. And compared to 0.1, we can assume X is going to be so small that this is just going to functionally approximate to 0.1. Now, I can't ignore X over here because I'm not comparing it to another number. This is still a very valid number when it's just by itself. But when I'm comparing it to another value in an addition or subtraction, I can pretty much ignore it. So, if I set up my Ka expression, where Ka is the concentration of H3O plus times the concentration of bicarbonate divided by the carbonic acid solution. And if I sub in my values, multiply both sides by the denominator, and take the square root, gives me a value of x is 2.07 times 10 to the negative 4. So that's my value for x. I can come back and bring that over here. This is 2.07 times 10 to the negative 4. There's my H3O plus concentration from the first deprotonation. Now, we should look at what happens with that second deprotonation. So I'm going to go ahead and erase this part. Let's look at that second deprotonation reaction. So my reaction now is bicarbonate reacting with water, acting like an acid to form hydronium ions, and now the carbonate ion, CO3 2-. My initial conditions. I know X was my initial or my equilibrium concentration of bicarbonate. So this is 2.07 times 10 to the negative 4. We don't care about liquid water. And like in the sulfuric acid example, now since I am doing the second deprotonation, I actually already have hydronium ions present. And their concentration we calculated to be 2.07 times 10 to the negative 4. And we have 0 carbonate at the beginning. My change is minus x. I don't care, plus x, and plus x, and at equilibrium, this is 2.07 times 10 to the negative 4 minus x, I don't care, 2.07 times 10 to the negative 4 plus x, and x. However, if I look at my Ka2 value, this is 5.6 times 10 to the negative 11. This is an exceedingly small value of Ka. Barely any of this has got turned into products because K is an extremely small number. So if K is very small, very little of this got changed. X is going to be insignificantly small. We're just going to assume this is still 2.07 times 10 to the negative 4. Same applies here. Compared to this number, x is going to be so small that this is still functionally 2.07 times 10 to the negative 4. And this is still x. So that'll give me my hydronium ion concentration. So the pH which is the negative log of the hydronium ion concentration equals the negative log 2.07 times 10 to the negative 4 gives me a pH of 3.68. So what we see here is when we are doing with polyprotic acids, if we're looking at weak acids, and we know we're looking at weak acids because the Ka values are very, very small. And this is especially true when those Ka values are 10 to the negative 4 or smaller. When we are looking for the pH of these weak polyprotic acids, really we only need to solve the Rice table for the first deprotonation. Because after that, the second and third deprotonations really aren't contributing very much to the hydronium ion concentration. They do affect it, but it is so negligible that it really does not affect our final answer. So, if you're given multiple pKa's or multiple Ka's for a polyprotic acid and you need to solve for the pH, you really only have to do it for the first step, the first deprotonation, because that'll give you the functional amount of hydronium ions. So that will wrap up our discussion on polyprotic acids. Thank you guys for being patient.